Hey guys, today we are doing our notes on liquids. So it's going to be a couple different ideas here. We're looking at pressure in general, pressure specifically in a liquid, buoyancy, which stems from Archimedes' principle, kind of what makes things float or sink. Obviously some flotation stuff with that, and then Pascal's principle, which is distribution of pressure at different liquids for different liquids. So, pressure, we've talked about this already a little bit, but just to formalize it, pressure we know is force per unit area that one object exerts on another. So, we know that it's force over a given area. The units depend on what units were given for our force and for our area. Standard units are newtons per square meter. We also have pounds per square foot. We also have pascals. We looked at a couple different pressure units on that gas laws worksheet from last week with torrs and atmospheres and stuff. But we have a lot of different units for pressure. Here, this is a nice example of pressure. You've probably seen these on TV shows or in anywhere. The nail bed, people that are laying on nail beds, or even this here, an extreme case of someone getting a cinder block crushed on top of them with laying on a bed of nails with a kind of shirt of nails on top of it. This doesn't hurt them at all because that pressure that they're exerting is distributed over a great number of points. So it's not just a single nail that's being driven in with that amount of pressure, with that amount of force. It's because it's distributed over many different nails that it's not going to hurt them at all. So we're going to be doing these a couple of different times throughout the video, so if you need to pause these to answer the questions, feel free to do so. Here, just a little personal check. If you're remote and watching this on your own, feel free to just answer these yourselves. If you're here in person, Sam, Tyler, feel free to go ahead and pause this and then answer the question to each other and have a little discussion, and we'll see if you're correct or not. So our question here, when you're standing on 1 foot instead of 2, the force you exert on the floor is less, the same, more, or none of the above. So if you stand on 1 foot instead of 2, what happens to the pressure, the force you exert? Sorry, the force you exert. Okay, our answer should be that it's the same. The force itself is not any different. The difference between force and pressure is what we're looking at here. The force stays the same. The mass times gravity, right? Mass times acceleration of our body is the same pulling down, whether we're standing on 1 foot or 2. Now, this is much different if we're standing on 1 foot instead of 2. The pressure we exert is actually going to be more. Right? C should be our correct answer here because it's actually twice as much. We have the same amount of force over half of the area. So if we're assuming that our feet are the exact same size, if we're standing on 1 foot instead of 2, all of that force is over half of the area, so our force will double. Our pressure will double. Pressure in a liquid. So it's still like pressure is still force per unit area, but here in this case, it's just the pressure that the liquid exerts on an object. Here for pressure of a liquid, it depends on the depth, not the volume. So that's the really big important thing here. If we can swim, like if we have this giant, huge pool, but it's only 4 inches of water, it doesn't exert more pressure just because there's more volume than a glass of water that is 6 inches. Like if you have a 6-inch tall glass of water, the bottom of that would actually exert more pressure than a huge, massive football field-sized pool that's only 4 inches of water deep. It's all depth dependent, not volume dependent. Pressure in a liquid acts equally in all directions, which we'll talk about a little bit later, with kind of how things interact with each other. So if you if you poked a hole on one side of the cup, if you poked a hole on a different side of a cup, it all acts in the same direction, the same magnitude in all of the different directions. Here's some examples of liquid and pressure in liquid. Your ears feel the same amount of pressure underwater no matter how you tip your head. Right? If you go underwater, it's not like if you point your head up versus down, there's going to be more pressure pushing down on your ear versus pushing up on your ear. It's the same exact pressure experienced. The bottom of a boat pushed upward by the water pressure. Pressure acts upward when pushing a beach ball underwater. So it's not necessarily, again, pressure having to come from above like we will have with like atmospheric pressure. It's all equal in the same direction, or in all directions. Pressure is also independent from the shape of the container. So it doesn't matter what kind of container you're putting it in, the shape of the container has no impact on it. It's all still depth dependent. So I really wish I had one of these. You can see this lady is holding kind of a demonstration of that, where it doesn't matter what shape it is, doesn't matter the thickness of the container. You can see pressure is depth dependent. So all 4 of these different kind of stems or different containers within the same kind of common whatever container is the word that I'm going to use. They're all the exact same depth, no matter what the size is, no matter the angle or the volume that it takes up. It equalizes because that pressure is depth dependent, not volume dependent. So liquid pressure, we have an equation for that, a formula for that. It's the density of that that liquid, so the weight density times how deep it is. That tells us what the liquid pressure, or what the pressure would be exerting at that particular depth. So question here, another little quick check on pressure in liquid. Water pressure provided by a water tower is greater if the tower is A, taller, B, holds more water, both A and B, or D, none of the above. So a water tower provides pressure by having water up in the tower and then using that obviously to flow downward. Which one of these is going to have an impact on the pressure? The correct answer here should be a taller water tower, right? Well, like we talked about, liquid pressure is depth dependent, not volume dependent. So adding more water to the water tower, making it a bigger bigger water bulb, I guess, tank up top, isn't going to increase the water pressure as much as it would be if we were to just make it taller. And like I said, depth dependent, not the amount of water that contributes to your pressure. All right, pressures in a liquid. Like we talked about, pressure works equally in all directions. So if we have something in the water, it acts equally in all of the different directions, but water pressure acts perpendicular to surfaces. So we know it works kind of in all different directions. It acts equally in every direction, but if it's dealing with something where it's the pressure is being exerted on an object, either on the side of the glass or on an object that's submerged in that water, that pressure acts perpendicular to the surface. So you can see here this triangle, the pressure is acting perpendicular against the 3 walls of the triangle. Here are example for the glass that has some holes cut in it. You can see that the pressure is exerted, like the water pressure is exerted perpendicular. Now, the angle that this water takes is pressure dependent, which means it's depth dependent. So you can see the deeper you are in the cup, the more pressure it's able to exert because it's a greater depth, which is why it comes out faster and has a steeper angle of departure for that liquid that's being kind of squirted out. All right, buoyancy. Buoyancy, we watched the Bill Nye video on Friday on this, but buoyancy is an apparent loss of weight of a submerged object, and that amount of buoyancy that it experiences is equal to the amount of liquid that is displaced. Now, I say liquid, on the notes here I know it says water, because most of the time we're submerging stuff in water, but if you're able to submerge it in other liquids, it actually would have a different buoyancy than if you submerge it in water, because the density of water is different than the density of other liquids. So the amount of weight that is displaced is how much buoyant force we experience. Which is kind of getting into our displacement rule. A completely submerged object always displaces a volume of liquid equal to its own volume. So if we, submerged in this case, a potato in a container that is up to the brim in water, the amount of water that overflows is equal to the volume of the potato. Which, again, in the Bill Nye video, he talked about this. Archimedes, the one who took and measured the volume of the crown, I think is what it was. I mean, he told the story about him getting in a bath and then the water overflowing and then he was running through the streets naked or something. Some weird story, but it's Bill Nye, so awesome. But yeah, this is what we're talking about here. So the volume that the potato takes up, the actual space that takes up, would be displaced by the water. That weight of water is how much buoyant force the potato would experience. Okay, so another check here. A cook who measures a specific amount of butter by placing it in a measuring cup with water in it is using the A, principle of buoyancy, displacement rule, B, C, concept of density, or D, all of the above. So again, if he's looking at how much water, measuring an amount of butter by placing it in a measuring cup with water, he's of course using the displacement rule. We're looking at how much water is displaced, how much my volume changes in that measuring cup would tell me how much volume of butter that cook would have. All right, buoyancy in a liquid. We talked about this just a minute or so ago. The net upward force that a fluid exerts on an immersed object is equal to the weight of water displaced. So again, if we look at the volume of this square, if we knew how much volume it was, we could look at how much water it then displaces, how much weight it displaces in water, and that would tell me how much buoyant force it experiences. The difference between your upward and your downward forces acting on the submerged object is the same at any depth. So as we go deeper and deeper down, my pressure downward is greater, but my buoyant force upward is also proportionally greater. So my net force acting on an object is going to be equal at any depth. Because again, the deeper you go down, there's going to be more pressure, because again, it's equal in all directions. There's more pressure going down on the object, but there's also another amount that's increased as we go deep for the amount of water that's displaced as well. Another check-in here. How many forces acting on a submerged body at rest in a fluid? I read that wrong. How many forces act on a submerged body at rest in a fluid? So do we have one force, which is just buoyancy? Do we have two forces acting on an object, buoyant force and the force due to gravity? C, none, and according to the equilibrium rule, your net force has to be 0. Or D, none of the above. Okay. Obviously here it has to be two of them. It is gravity and the buoyant force. Gravity pulling down, buoyant force pushing up. All right, so the big question when we're talking about buoyancy, does it sink or does it float? Well, we've got the two different options. There's a lot of different variables that go into this, but in a nutshell, it's going to sink when the amount of water that's displaced is greater than the buoyant force. So if the object weighs more than the amount of water it displaces, it's going to sink. So if you have a rock, if you have some, depending on the shape of the object, if you have something where the volume of water it displaces, so let's just say we've got a 1 cubic meter, well, that would be huge. 0.5 cubic meter rectangle or block of metal that weighs, 3 or 4 kilos. When I submerge it in water, if the amount of water is only 1 kilogram of weight in terms of the water that's displaced, it's going to sink because there's more weight pulling it down than there is pushing up against it. If your objects are equal in density, your objects, as in like your object has the same density as water, it's going to displace as much weight as it does acting on it. So they would neither sink nor float. It would just kind of be suspended there at that level. So it's not gonna rise up and float up to the top. It's not gonna sink down to the bottom. It's just gonna be suspended there in the liquid. And that happens again when the object has the equal density of the liquid that it's in. And of course it floats when the weight of the submerged object is less than the buoyant force that it would have when it's submerged. So when floating, your buoyant force is equal to the weight of the floating object. All right, so Archimedes' principle. So Archimedes is that super old, smart, dead dude that we talked about, or that Bill and I talked about in kind of his idea of buoyancy and stuff. He's the one who discovered the displacement rule for buoyancy, which states that in an immersed body, completely or partially, that is buoyed up by a force is equal to the weight of the fluid that it displaces. This applies to both gases and liquids. So gases and liquids are both fluids. They both exert the same thing. So Archimedes' principle in terms of buoyancy still applies as well. That's how balloons float, because when you're looking at a helium balloon that's filled, a balloon that's filled with helium or some light gas, the amount of mass, or the amount of weight of gas that it displaces in our atmosphere is greater than the weight of what's inside it. So that happens again when the density of that gas that's inside your balloon is less than the density of our atmosphere. Yeah, apparent weight of a submerged object, weighing it out of the water versus the buoyant force. Here we can see a 3 kilogram block submerged in water apparently weighs 2 kilograms when the buoyant force is, sorry, you can see out of the water if it weighs 3 kilograms. So that's the apparent weight. If you submerge it and now it only weighs 1 kilogram, that means it had to displace 2 kilograms of water. Because again, the total amount of buoyant force plus the force downward that's acting on the object once it's submerged has to be equal to what was beforehand. On which one of these blocks submerged in water is the buoyant force the greatest? So we're looking at which one has the greatest buoyant force. A kilogram of lead, a kilogram of aluminum, a kilogram of uranium, or is it all the same? So this one's a little bit tricky because if you're looking at buoyant force, we have to look at the volume that's displaced. So we have to look at which one of these weights have the largest volume, which means which one of these is the least dense. We know that aluminum is less dense than lead. Uranium is the most dense of all three of those, so my answer should be aluminum. Again, the largest block of one that has 1 kilogram of mass is the aluminum one, which means it displaces more water, which means it has the greatest buoyant force. When a fish expands its bladder, the density of the fish, if it's going to expand its bladder, that means, so they have little air sacs, air pockets in most fish that they can kind of expand or submerge, little ballasts, kind of the same thing in like a submarine, that they can inflate with air, which would then mean they have a greater volume for the same amount of mass, so their density, of course, would decrease. It makes itself less dense, which means the buoyant force on it is going to, come on, oh my goodness, increase. Goodness gracious. Yeah, so if it's less dense, it's displacing more weight of water for the same amount of mass, so it's going to increase its buoyancy. And if it increases its air bladder, if it decreases the size of its air bladder the other way around, the density is going to increase. Same idea here. I already talked about this. A submarine takes water into its ballast tanks. So those ballasts are kind of like air pockets. So they have these little tanks on a submarine that can be they can either let water in, or they have pumps that can pump water out, and then it's just replaced with air. So that it allows it to kind of adjust its density and dive to different depths, which is kind of cool. But when it takes water into the ballast tanks, it's going to increase the weight, which means it's going to increase the density. If it pumps water out of the ballast, it's going to decrease the density. That's how it works to be able to kind of work on all these different levels of depths for submarines. All right, Archimedes' principle of flotation basically says, again, if the weight of the water that if it's displacing is equal to its own weight, it's going to float at the surface. So here it allows you kind of increasing the surface area, the volume of water that is displacing with the same amount of material allows us to be able to make things that wouldn't necessarily float if it was just raw material to float using these different more sturdy materials. So you can see here this weight of iron that is the exact same weight is pulling down, but here since it's just a block of iron that's sinking, but if I took that same iron and made this boat shaped, this kind of elongated U shape, because the volume of water that I'm displacing is increasing with the same amount of weight, it's able to float instead of sink. All right, so for check-in here for this next one, the reason a person finds it easier to float in salt water compared to fresh water is that in salt water, the buoyant force is greater. A person feels less heavy. Neither of these or none of the above. Which, I guess neither of those two versus none of the above. It could be for a different reason. It's weird the way I have that phrase. Yeah, neither should be the answer here. The reason that someone feels finds it easier to float in salt water is basically because of the density. So we've talked about how the amount of the weight of the water, the weight of the liquid that we displace is the amount of buoyant force that we experience. And in salt water, because it's water and salt, it is more dense than regular fresh water. So because it's more dense, the same volume of water that's being displaced by our bodies weighs more, therefore we experience a greater buoyant force. On a boat ride, a skipper gives you a life preserver filled with lead pellets. When he sees the skeptical look on your face, he says that you'll experience a greater buoyant force if you fall overboard than your friends who wear styrofoam-filled life preservers. A, he apparently doesn't know his physics, or B, he's correct. Which one of these two? He says that life preserver filled with lead pellets is going to experience a greater buoyant force if you fall overboard than the styrofoam-filled life preservers. He's actually correct, but what he doesn't tell you is that you're going to drown. The life preserver will submerge and displace more water than your friends who will float on the surface. So technically, because it sinks down, it will displace more water, which means it does experience a greater buoyant force, but the net force that you're experiencing is still greater downward than it is upward. So while he is correct, he is also incorrect and an idiot. He should not be trusted. Why is this man the skipper of a boat? Next question here, flotation. If you place an object in a container that is full to the brim of water on a scale, the object floats, but some water spills out. How does the weight of the object compare to the weight of the water that is displaced? We've got 4 different options here. The weight of the object is greater than the weight of the water displaced. The weight of the object is less than the weight of the water displaced. The weight of the object is equal to the weight of the water that's displaced, or there's not enough information. In this case, the correct answer should be C. The principle wonderfully illustrates here what we're going to see here in just a second. Scotland's Falkirk wheel. Once it's at equilibrium, so once it's kind of floating there, it floats and it reaches equilibrium with the weight that's pushing down on it and the force that's pushing up on it. Sorry, the force pushing down on it and the force pushing up on it have equalized when it's floating there at the surface. So however much water was displaced in order to provide enough buoyant force to float is equal to the weight of that block before you actually put it in there, which is interesting. So this is kind of cool. This is the Falkirk wheel. It's got 2, I don't know how to pronounce, caissons, 2 basically little tanks of water that are full to the brim that have the same weight. So when boats go in there, it displaces water that is equal to the amount of weight that it originally had with it. And then so it's able to actually turn because those 2 weights are equal to each other. And the boat is, basically it's a water bridge. But it's a raised water bridge, which is super cool because you can see like that when the GIF will start over here in a second. There we go. So the ferry kind of goes in there. It is able to rotate in because the amount of water that's displaced is equal to the weight of the boat that goes into that particular tank, and then it's able to continue along its path up top, which is super, super cool. All right, so Archimedes' principle. Denser fluids will be greater, will exert a greater buoyant force on a body than less dense fluids, which would be the same. Again, anything that will float in salt water, which is 1.03 grams per cubic inch, it floats higher than in fresh water because fresh water has a density of 1 gram per cubic centimeter. As I talked about earlier, Archimedes' principle also applies to air. It's still a fluid. It flows freely. There's no, it fills the volume of the container that it's in. The more air that an object displaces, the greater the buoyant force will be on it. So if an object displaces its own weight, it hovers at a constant altitude. If an object displaces less air, it descends. So it sinks in the air. So as you sit in class, is there a buoyant force acting on you right now? Two choices. Nope. As evidence of the absence of lift, I'm not floating, I'm not raised up at all, I'm not experiencing any buoyant force. Or yes, there is buoyant force due to the displacement of air. The correct question, of course, is yes, even though there is a buoyant force on it because our mass compared to the weight of the air that we're displacing is so far skewed, we don't experience any buoyant force. Like we're not necessarily experience, but we don't perceive the buoyant force because it's so small compared to the weight that we are being pulled down by gravity. But there is a buoyant force that's acting on us. What makes an object sink or float? We already talked about this. It depends on two things: the object's volume and the volume of the object, or the fluid that's displaced. So then that tells you kind of the weight of the object that is less than the buoyant force of the liquid. Then it's going to float. We've already talked about this. I don't know why I'm rehashing these. So we've got three different rules here for if an object is going to float or if it's going to sink. If an object is more dense than the fluid in which it's immersed, it will sink. So if it's more dense, it's going to sink. If it's less dense, then it's going to float. And then objects having the equal density of the fluid that it's in will be immersed and will not sink or float. It just kind of is suspended in that liquid, that fluid. All right, last couple of slides here. Two solid blocks of identical size are submerged in water. One block is lead, the other is aluminum, upon which is the buoyant force greater. So we've got exactly the same size blocks in terms of the volume of them. We're asked which one has the greater buoyant force. Is the buoyant force greater on the lead block, the aluminum block? Is it the same on both blocks, or is there not enough information to decide? And in this, they are the same in both blocks, because remember, your buoyant force depends on the volume of the block that is submerged, because it's dependent on the amount of weight of that liquid that's being displaced. And since their volumes are the same, they're going to displace the same amount of water, or the same amount of whatever the liquid is that's being displaced. So they experience the same amount of buoyant force. All right, last idea here, Pascal's principle. So Blaise Pascal, he's a scientist and a theologian, so a little bit of theology, religion stuff from the 17th century. His main discovery, Pascal, so if you remember, we were doing those pressure conversions back in the gas laws worksheet. Pascals is one of our units of measurement for pressure. It was named after this guy, Blaise Pascal. Pascal's principle states that if you have a change in pressure at any point in an enclosed fluid, so if you've got a container, like if you've got a syringe, or here, this example here, if you have any kind of change in pressure at one spot in the enclosed fluid, it does the same thing at all points. So if I increase the pressure at one point, every other point along that container experiences that equal amount of pressure. So basically, it applies to all fluids, both gases and liquids. If we press down at one spot, the rest of the container experiences the same thing. Which this is actually how hydraulics work. So in a hydraulic system, you have a small input of pressure on a small area that's connected to a much larger output. And here, so you can see here the example here, we have 10 kilogram mass pushing down on this part of this piston in our system. And because that pressure, so this weight time, or this force times area is whatever this ends up being, 10 times 9.8 times whatever this area is, but whatever this is, this area, is an input value. The pressure that it's exerting there at that small little input area is amplified across this entire huge area. And just a 10 kilogram mass is big enough to lift a 500 kilogram mass, because this area, the output area, is 50 times larger than the input area. So this is actually how hydraulics work. You're able to compress. So here, this is a hydraulic system. You've got a compressor that pushes air into the reservoir, which forces this little input area, forces some liquid down into it, and that increase of that pressure in that tank actually increases the pressure across the rest of this piston, which is how hydraulics work. You're able to take these small input volumes and small input pressures and amplitude, like magnify it over a greater area and do a whole lot more work than what the work in is, which is kind of cool. So for our second to last question here, or actually this is our last question. In a hydraulic device, it is important for the output piston to move farther out than the input piston. Is it important for the force output to exceed the force input? Is it important for the output piston speed to exceed the input piston speed, or the energy output to exceed the energy input? So for a hydraulic device, of course, we want the energy in to be less than the energy out. We want to put a little bit amount of pressure in, a little bit amount of energy in to get a much greater result on the backside, which is how hydraulics work. That's all I have for you guys for liquids. So as always, if you guys have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys are reaching out and letting me know. Otherwise, have a fantastic day. We'll see you soon.